In the vast, silent theater of the cosmos, there are explosions. And then there are hypernovae. Imagine an event so violent, so titanically powerful, that in a few seconds it unleashes more energy than our sun will produce over its entire 10 billion year lifetime. An explosion so brilliant it can outshine its own galaxy, a swirling city of hundreds of billions of stars. This isn't science fiction. This is the universe at its most extreme. This is what happens when a cosmic titan, a star more than 30 times the mass of our sun, collapses under its own impossible weight. But this extraordinary act of destruction is also a moment of creation. Because from this inferno, from the stellar ashes of this cataclysm, something entirely new is born, something dark, something inescapable, something that will bend the very fabric of space-time to its will. Today, we're going to unravel the mystery of the hypernova and show you how the universe's most powerful explosion forges a brand new black hole, the doomed Titan. Before the explosion, before the black hole, there's the star. And this is no ordinary star. It's a giant, a behemoth of blue-white fire, a true monster of the cosmos. To even be a candidate for this spectacular death, a star has to start its life with at least 25 to 30 times the mass of our own sun. Just think about our sun for a second. A star so big you could fit over 1 million Earths inside it. Now imagine a star 30 times more massive than that. The gravitational force of an object like that is almost impossible to wrap your head around. This immense gravity defines every moment of the star's life and seals its ultimate fate. While our sun will burn gracefully for 10 billion years, these stellar titans are the universe's ultimate rock stars. They live fast and die young. A star this massive burns through its nuclear fuel with a reckless, furious intensity. You can think of it like a cosmic drag racer that floors the accelerator, burning its entire fuel tank in a stunningly short time. Our sun is a slow, steady burn. A massive star is a raging inferno, shining thousands of times brighter and living for only a few million years. That's just a blink of an eye in cosmic time. Deep inside its core, a dramatic story of creation is playing out. The star's whole life is a desperate battle, a cosmic tug-of-war between two fundamental forces. On one side, you have gravity, relentlessly trying to crush the star into the smallest possible point. On the other, you have the outward pressure from nuclear fusion, the star's engine. This engine starts by fusing hydrogen into helium. When the hydrogen runs out, the core contracts and heats up until it's hot enough to fuse helium into carbon. Then carbon into neon, neon into oxygen, oxygen into silicon. With each stage, the star acts like a celestial alchemist, creating heavier and heavier elements. But here's the catch. Each new fusion stage provides less energy and happens faster and faster. The hydrogen-burning phase might last for millions of years, but the final silicon-burning phase, it lasts for less than a day. Eventually, this cosmic assembly line produces the one element that signals the end: iron. For a massive star, iron is ash. It's a nuclear dead end. Unlike all the elements that came before it, fusing iron doesn't release energy. It consumes it. The star's engine, which fought against gravity its entire life, suddenly and catastrophically switches off. The cosmic tug-of-war is over. Gravity wins. The collapse. What happens in the moments after the star's core turns to iron is one of the most violent events in the known universe. With its energy source gone, there's nothing left to hold back the colossal weight of the star's outer layers. The result is a collapse so rapid and complete it's hard to even visualize. The iron core, an object already more massive than our sun but squeezed into a ball the size of Earth, begins to implode. It collapses in on itself at incredible speeds, reaching up to 1/4 of the speed of light. The star's heart is falling inward, shrinking from the size of a planet to the size of a city in less than a second. Now, for a smaller star, this collapse would be stopped. The imploding material would crush together so tightly that protons and electrons would merge, creating an incredibly dense ball of neutrons. This neutron star would push back, creating a shock wave that blows the star's outer layers apart in a normal supernova. But our star isn't normal. It's a titan. Its core is just too massive. The weight of all that material crashing down is so overwhelming that not even the physics that govern neutron stars can stop it. The collapsing core blows right past the neutron star stage. There is no force left in nature strong enough to halt this ultimate collapse. The core just keeps shrinking, crushed down to a point of zero volume and infinite density, a singularity. In the heart of the dying star, in a fraction of a second, a black hole is born. It's a quiet, terrifying moment. The star's core has effectively vanished from the observable universe, leaving behind only its immense gravity. But the rest of the star, tens of solar masses of gas and plasma, is still hurtling inwards, completely unaware that its center has been replaced by a monster. And this is where the real show begins. The death of this star isn't a supernova. It's something far more powerful, something that needs a brand new engine of destruction. This moment, where a star's heart is replaced by a black hole, fundamentally changes our understanding of the cosmos. If you find this journey into the heart of a cosmic titan as fascinating as we do, and you want to support our channel, please consider liking this video and subscribing. Your support is what allows us to keep exploring the universe's biggest questions. The engine of destruction. So we have a brand new black hole sitting in the heart of its parent star, which is still collapsing around it. What happens next isn't a spherical explosion. It's a targeted, focused demolition job powered by the most extreme physics imaginable. This is all explained by a theory known as the collapsor model, and it's the key to how a hypernova really works. The first ingredient is, of course, the black hole, but the second, equally crucial ingredient, is spin. The original star was almost certainly rotating. As it collapsed, like an ice skater pulling in their arms, that rotation sped up dramatically. This means the material now falling toward the new black hole isn't falling straight in. It's spiraling. This spiraling material forms an enormous, incredibly dense, and unimaginably hot structure around the black hole's equator, an accretion disk. Think of it as the most violent whirlpool in the universe. Matter in this disk is revved up to near light speed, heated to billions of degrees, and crushed by tidal forces. This disk is the engine of the hypernova. As this superheated plasma swirls around the black hole, it drags the black hole's magnetic fields along for the ride. The rotation twists these magnetic fields into colossal, tightly wound funnels pointing away from the black hole's poles. These magnetic funnels effectively become cosmic particle accelerators. They start grabbing a tiny fraction of the infalling material from the disk and channeling it. They accelerate this plasma outward along the black hole's axis of rotation, away from the poles. This isn't a gentle stream. It's a pair of tightly focused, ferocious jets of matter and energy moving at over 99% the speed of light. These are relativistic jets, and they are the lit fuse in the heart of the dying star. The black hole and its disk have become an engine, converting the gravitational energy of the collapsing star into two of the most destructive beams in the universe. Now, all that's left is for those beams to get out. The hypernova unleashed. Right now, these jets are still trapped deep inside the star. They are two beams of unimaginable power, firing from the core, and they have to punch their way out. What follows is a scene of pure cosmic violence. The jets, narrower than a laser pointer in cosmic terms but carrying the energy of trillions of nuclear bombs, start drilling through the star from the inside out. They tear through the dense layers of silicon, oxygen, carbon, and helium that are still falling inward. This journey isn't instantaneous. It takes several seconds for the jets to travel from the core to the star's surface. During that time, they are like a blowtorch cutting through steel. The interaction between the jets and the stellar material creates a cocoon of superheated plasma and radiation, pushing outwards and sending shock waves that start to shatter the star. Finally, the jets burst through the star's surface, and this is the moment the hypernova truly begins. The second the jets break free, they unleash an incredible flood of energy. First, a torrent of high-energy light, specifically gamma rays. If one of these jets happens to be pointed directly at Earth, our telescopes see an intensely bright flash of gamma radiation. For decades, these were a mystery, known only as long-duration gamma-ray bursts, or GRBs. Now we know what many of them are: the birth announcement of a new black hole. They are the death cry of a massive star. In fact, the archetypal hypernova, SN 1998 BW, was directly linked to a gamma-ray burst, confirming the connection. But the hypernova is more than just gamma rays. The energy from the jets doesn't just travel into space. The powerful shock waves created as the jets drilled through the star now blast sideways, ripping the rest of the star to shreds. This is the visible explosion of the hypernova. It's typically 10 to 50 times more powerful than a regular supernova, and in the most extreme cases can be 100 times more energetic. The explosion is so energetic it triggers one last furious round of element creation. It forges huge quantities of heavy elements, including vast amounts of radioactive nickel-56. It's the decay of this nickel that powers the hypernova's incredible brightness, causing it to glow with the light of an entire galaxy for weeks. The light from this explosion also has uniquely broad spectral lines, a smoking gun indicating that matter is being ejected at phenomenal speeds, driven by that central jet engine. So, a supernova is the explosion of a dying star. A hypernova is the explosion of a dying star powered by a black hole engine at its center. It's not a spherical blast, but a two-sided one, driven by jets that shred the star from the inside out. It's a collapsar, and it's the most extreme stellar death the universe has to offer. The aftermath and the ghost. Over the following weeks and months, the brilliant light of the hypernova finally fades. The vast clouds of newly forged elements expand into interstellar space, a ghostly, glowing remnant of the Titan that once was. And when the cosmic dust settles, what's left at the heart of it all? A spinning, stellar mass black hole. The ghost of the star, the quiet engine that drove the whole cataclysm. In some cases, the explosion might not be powerful enough to blow away all of the star's material. A significant amount of matter can fail to escape and fall back onto the newborn black hole, causing it to grow even more massive in the hours and days after its birth. So, the hypernova was never just an explosion, it was a birth. The gamma-ray burst was its first cry. The blinding light was the afterglow of a violent delivery, and the expanding nebula of gas and heavy elements is the placenta, enriching the galaxy for future generations of stars and planets. Every time we see a long-duration gamma ray burst from across the universe, we are witnessing this exact process. Recent simulations even predict that the chaotic spiral of matter into the new black hole should produce its own unique signature of gravitational waves, ripples in space-time itself. Future detectors might one day let us listen in on these incredible births. The story of a hypernova shows you the dual nature of the cosmos. It's an event of unimaginable destruction, the complete annihilation of one of the universe's most massive creations. Yet, from that violence comes profound creation. The black hole it leaves behind becomes a new gravitational anchor, a fundamental building block of the galaxy. The hypernova itself is a crucial engine of cosmic evolution. Its powerful shock waves can trigger the collapse of nearby gas clouds, kick-starting the formation of new stars. The jets are suspected to be a source of the mysterious ultra-high-energy cosmic rays that rain down on Earth, particles accelerated to energies far beyond anything we can achieve on this planet. And maybe most importantly, hypernovae are galactic seed spreaders. They blast the universe with heavy elements forged in the star's life and the explosion's fire. The iron, the zinc, the gold, These are elements essential for forming rocky planets, and ultimately, for life. The very materials that make up our world and even our bodies were forged in the hearts of stars and scattered by explosions just like this one. As we continue to peer into the cosmos with instruments like the James Webb Space Telescope, we're getting a clearer picture of these extreme events. But each observation refines our understanding and deepens the mystery. It makes you wonder. When we look up at the night sky, we see points of light that represent the past. How many of those distant, unassuming stars are actually cosmic time bombs, getting ready to unleash the next hypernova? What other secrets about our universe are hidden in the light of its most powerful explosions? If you want to keep exploring the most extreme phenomena in the cosmos with us, from the birth of black holes to the fate of the universe itself, make sure you subscribe and turn on notifications. And check out our other video on the different kinds of supernovae to see how they compare. Thanks for joining us.